This lecture is going to be a bit different than our other lectures. At this point, I think you have a pretty good understanding of the basics of finite difference time domain. What we're going to do now is generalize some of our concepts, build some other tools, and change our finite difference time domain analysis so that we're doing something completely different. Rather than looking at transmission and reflection from a device in terms of plane waves, we're going to look at waveguide circuits, learn how to source those with specific modes in the waveguide, so we'll also need to analyze the waveguide and see how much of the different modes come out on the other side of our waveguide circuit. So to get into this, what we'll need to do first is learn about slab waveguides and how to analyze them. We need to calculate the modes that exist in a slab waveguide, first order, second order, third order, that type of thing, because we may want to excite a waveguide selectively with one of those modes or some combination of those modes. And when our field comes out on the other side of our waveguide circuit, we want to figure out how much power is in each of those modes. And that all starts off with a frequency domain analysis to calculate the modes. We'll then use those to source the waveguides in our finite difference time domain, and it's a generalization to our total field scatter field that we've been talking about. And then ultimately, how do we calculate transmission and reflection from the waveguides and how much power is in each of the modes individually. So on to just more of a theoretical discussion of slab waveguides. First, we are going to do a two-dimensional simulation of a waveguide circuit. Simple one. We'll actually step through a waveguide bend, but they can be more complicated. And in reality, these are three-dimensional devices. And I know I've talked through this procedure. I'll discuss it one more time, but we want to reduce what is really a three-dimensional problem down to a two-dimensional problem. So what we'll do is we'll look at the cross-section around our rib in this waveguide and calculate some effective refractive index. And then we'll go away from our guide and calculate some other effective refractive index. And by using these two, we can construct our waveguide circuit on a two-dimensional grid that pretty accurately predicts the behavior of a fully three-dimensional model, but with much, much more efficiency. So what causes waveguiding? Well, the biggest aspect of this is total internal reflection for a dielectric waveguide anyway. So if we have a wave going from a high index material into a low index material, we have some magical angle called the critical angle. And when our angle of incidence is less than the critical angle, we get some transmission. When that angle of incidence becomes greater than the critical angle, we don't get any transmission. And in fact, it 100% reflects for all angles greater than this critical angle. So using this technique, if we have a high index region sandwiched between two low index regions, and we have a large enough angle on each of those, we can get a wave to sort of stay confined in this high index region, sort of bounce between both of the interfaces. So here's a picture of that situation. We have this high index region surrounded by two regions that don't necessarily have to be the same, but both of these have to be lower than the core, and we'll get total internal reflection off of both interfaces. So this is called a slab waveguide. We're only confining energy here vertically. Within the plane of the slab, the power can go whatever direction it wants to. When we confine it in two directions and we have more like a pipe, that is a channel waveguide. Another thing we can get from a ray tracing analysis, we have to realize that if we look at the field at one point in its round trip and we go and we find that equivalent point, it has to accumulate an integer multiple of 2 pi phase from like point to like point. If it's anything other than an integer multiple of 2 pi, it interferes with itself, and in fact it leaks out of the guide. It's not a supported guided mode. So based on this, we can, just from a ray tracing perspective, understand there's really only discrete directions that will satisfy this. And in fact, guided modes are discrete. There's no continuum of supported guided modes. They're very discrete. And we need to calculate those, and we'll have first order, second order, third order modes. Now the ray tracing is good for a quick, fast, sort of qualitative understanding. We need to get much more rigorous about this. We need to analyze our slab waveguide rigorously because our source and finite difference time domain needs to be pretty darn close to a rigorous solution. So we'll calculate these modes, and then given that, we can excite any combination of those modes that we want to into our waveguide. And we also need the same analysis to figure out on the other end how much power ends up in each of those modes. Waveguide discontinuities, whether it's bends or some kind of bump or anything like that, can scramble energy between the different modes, and we might need to distinguish how much power ends up in each of those modes and calculate how much energy goes from one mode into the other, etc. So we start at the same place we always do, and we start with the equations that we had for finite difference time domain, but we want to analyze these in the frequency domain. So first thing we'll do is convert these from the time domain to the frequency domain. We'll also take this constitutive relation, substitute that back into our curl equations, and we end up with two equations just with E and H. We then take these two curl equations, which are vector equations, and write them as a set of 6 coupled partial differential equations. We did a similar thing here when we were deriving update equations for finite difference time domain. So we have 6 equations we'll call, or still call, Maxwell's equations. Now we need to know a little bit about the modes themselves. And let's look at the picture in the upper right. We have some crazy kind of waveguide. And it turns out no matter what the waveguide looks like, the modes have the same mathematical form. And if we look at the cross-section of this, the mode looks like potentially something crazy. However, it doesn't change from there unless there's a discontinuity in the waveguide. But for a straight uniform waveguide, this mode just looks like whatever it does, and all it does is accumulate phase according to e to the minus j beta y. But the amplitude in the cross-section stays the same. So in a way, propagation of waveguide is very boring. The only thing a little bit more interesting that can happen is we might have multiple modes. There's different amplitudes on each of those modes, but they propagate independently. They don't scramble energy unless there's something about the waveguide like a bend or a bump or something like that. Now they travel at different velocities because each mode has a separate propagation constant, and they may go in and out of phase, but their amplitude cross sections for each individual mode is just uniform, and nothing changes in the direction of propagation. So the mathematical form of our modes is shown at the upper left. The overall electric and magnetic fields as a function of x, y, and z has these amplitude terms, which is just in the cross section, in this case x and z, and then the propagation terms in the y direction. So let's think about what happens now when we take derivatives in this y direction. Very little is changing. There's no materials that are changing. These amplitude terms, they're not a function of y, only this propagation term. So let's go ahead and take the derivative of the electric field. So when we do that, we use the product rule, and we have the electric field times the derivative of our propagation term plus the propagation term times the derivative of the electric field. Well, remember the derivative of the y direction of this amplitude term is not a function of y, so this term completely crosses off and becomes 0. And of course we can real easily take the derivative of this complex exponential. So the moral is we take the derivative of e in the y direction, we get j beta e, the amplitude term, e to the j beta y, which is just j beta times the original electric field. If we look at the derivative of the magnetic field, we get the same exact thing. The answer is just j beta times h. So the moral here is anywhere we're taking the derivative in the y direction, we can pull this out and just replace it with j beta. So what we'll do is we'll go back to Maxwell's equations, our 6 Maxwell's equations, pull out our y derivatives, and put in j beta. Beta, remember, is the propagation constant of our mode. It describes how quickly it accumulates phase in the y direction. Now we want to look at the geometry of our slab waveguide. We will say that the waveguide and propagation goes in the y direction. The x-axis describes the cross-section of the slab, but then we have the z-axis going in and out of the screen here, and everything is uniform in the z direction, and the wave is not traveling in the z direction. So there's nothing changing in the z direction. So anytime we would take a derivative in the z direction, that has to be 0. So in our 6 Maxwell's equations, anything that we're taking a derivative in the z direction, we set to 0. Anything with the derivative in the y direction, we take out the partial derivative with respect to y and replace it with j beta. When we do that, here's where we end up. Now, at the top are the equations we ended with on the last slide, and now I color-coded them to show something. What happens to Maxwell's equations for slab waveguides is that it decouples into 2 independent modes, just like what happened with finite-difference time domain, but now it's slab waveguide analysis. You'll notice the equations I'm showing in red only contain EX, EY, and HZ. The blue terms don't contain any of those 3 components. Likewise, the blue equations contain HX, HY, and EZ, and none of those terms appear in the red equations. So let's separate them by color, and on the left we have the EZ mode, and on the right we'll have our HZ mode. So if we're doing an EZ mode in finite difference time domain, we'll need to use the EZ mode waveguide calculator to calculate our modes. And if we're modeling with the HZ mode, we need to use the HZ mode calculator to stay consistent. We wouldn't want to cross those because it turns out the modes look a little bit different for these. The waveguide modes look a little bit different for E and H modes. For frequency domain analysis, we'll also want to normalize our grid. So what we'll do is we'll multiply our coordinates by k0. So remember, k0 is 2 pi over the wavelength. So essentially what we're doing is expressing our coordinates in terms of wavelengths, but there's also this factor of 2 pi in there. And the reason we leave the 2 pi in there, multiplying by k0, it turns out that simplifies Maxwell's equations in a really good way. We also need to recognize our propagation constant beta is the same k0 term times the effective refractive index of our mode. And the way we interpret the effective refractive index, imagine we had a mode racing down our waveguide. If right next to it we had this infinite slab of dielectric and a plane wave propagating in it, if we want to see phase accumulating at the same exact speed, or these things traveling at the same speed, if you will, then the refractive index of that bulk slab needs to be n effective, the same as the effective refractive index in the waveguide. And then we would see that plane wave and the phase in the waveguide sort of travel at the same speed. So anyway, we can replace beta with k0 NEFF, and we can also normalize our grid, and when we do that, we get a very simple form of Maxwell's equations with normalized grids, and we have the effective refractive index in there. We don't know the effective refractive index. We'll formulate this, and in the end, it's our formulation that will tell us. We'll calculate by solving a matrix equation what that effective refractive index is. Okay, so now we're going to start getting into some linear algebra. At the end of this section, I provide all the MATLAB code you need to analyze a waveguide. So don't worry too much about the numerics here, but I do want to show it to you. It's interesting to know, and you'll have an idea of what's happening in the MATLAB code, but don't worry about absorbing everything. However, what we're doing here is very much like what we do in the following course to this called computational electromagnetics. So maybe it's a good introduction to that. So we want to analyze this waveguide numerically. We know we're going to have to express or put our waveguide on a grid. So we're storing values at discrete points. In this case, I'm showing electric fields at discrete points on a one-dimensional grid. We will store these in a column vector in a single file row. Likewise, if we had a two-dimensional grid, we can still raster through this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and list these in a single file column vector. In fact, no matter how many dimensions in our array, in memory it's always stored linearly anyway. So here we just reshape it to a linear array, so no matter how many dimensions we're representing, we can still store all of the unknown values in a column vector. So for our slab waveguide analysis, we're just using the one-dimensional grid. So, and here's a big step, and I will talk you through everything here, but suffice to say there's a little bit more to this, and we go into this in glorious detail in the computational electromagnetics class. But I will teach you in that class how to use the finite difference method to solve differential equations in the frequency domain. And the way the finite differences is taught in that class, it actually completely removes having to explicitly touch finite differences. And in fact, once you master the technique that I show you, we can jump immediately from our analytical equations to our equations in matrix form. And if we look at these, we can make a comparison and see what's happening. So, we have magnetic field components and electric field components stored across some kind of grid. We store those in column vectors, which I'm showing in these lowercase letters. So here h sub y is a column vector storing all of the h sub y components throughout our entire grid. Likewise, h sub x is all the x components of the magnetic field throughout the grid stored in a column vector. And E sub z is all the electric field components stored in a column vector. Now, the permittivity and permeability, we are doing a point-by-point multiplication here. So the way we store these, and in a way it's similar to a column vector, we have these distributed throughout a grid. We can reshape that to a column vector. However, we will stick that column vector down the diagonal of an otherwise zero matrix. It's zeros out here and zeros out here. So just numbers going down the diagonal, but these are reshaped to a one-dimensional array that are the permittivities throughout the entire grid, but then stuck into the diagonal of a matrix. And we do the same things for the permeabilities if we have those. We reshape these from whatever dimension grid we have to a one-dimensional array, and then stick that one-dimensional array down the diagonal of a matrix. And so we're left with maybe the more complicated terms. We have these derivative operators. In our original differential equation, we're taking the derivative of h sub y in the x direction. H sub y is in a column vector. This is, again, the derivative in the x direction operating on the h fields. So this is a big, ugly square matrix set up so that when we multiply that square matrix by h sub y column vector, we get a new column vector, which if we plotted it, we would see the derivative of the h sub y field. So what do these look like, and how are they populated? They look like this. They're banded matrices, and they essentially have two dominant diagonals. And if we take this big matrix, multiply it by h sub y, we would see the derivative. So maybe a bit more to this story, but that is something we cover in glorious detail in the computational electromagnetics class. But I think you have enough of a taste of this that you can kind of appreciate what's happening here and how we can go straight from the analytical equation to our matrix form equation. At this point, we want to derive a matrix wave equation. So in the last slide, we ended up here. These are our equations in matrix form. We'll take these second two equations and solve for hx and hy. So now we have hx and hy all in terms of ez. So now what we can do is take these expressions for hx and hy and substitute them back into this first equation, and we'll have one equation completely in terms of ez. So here's that equation. Here we did our substitutions, and we simplify algebraically, and we have everything just in terms of ez. Now if we stare at this long enough, hopefully at some point we'll recognize, hey, that's an eigenvalue problem. In fact, it's a generalized eigenvalue problem of the form ax equals lambda bx. So a and b in this case, a is this collection of terms, which ends up being a big ugly square matrix, and b is this matrix, which we know is a diagonal matrix. In this case, it will have the reciprocals of the permeabilities going down the diagonal. Lambda is our eigenvalues, and x is our eigenvector. So this is what the fields would look like, and this will be the effective index squared. So it's almost our propagation constant. So we went through a whole bunch of stuff, and here is our generalized eigenvalue problem. So we'll extract a slice from our FDTD grid, analyze it as a slab waveguide, and then we calculate the modes by solving this generalized eigenvalue problem. So once we construct A and B in MATLAB, we call a command eig, and this calculates all of the eigenvectors and all of the eigenvalues. So this V matrix, if we look at the columns, the first column will be the first eigenvector. And this is the thing that if we plotted it, we would see the fields. We would see what the modes look like. And then for each eigenvector, there's a corresponding eigenvalue. And these are always one-to-one. The first eigenvector goes with the first eigenvalue. Second eigenvector goes with the second eigenvalue. And the eigenvalues from our equation is the effective refractive index squared. So in fact, this is the effective refractive index for the first mode in our eigenvector matrix. Second eigenvector, second eigenvalue, and so on. Remember, this has the form for slab waveguides. This column vector is this amplitude term, and that's just in the x direction. And then our eigenvalue gets stuck into this exponential as this. So our eigenvalues come off as effective index squared. We take the square root of it and stick it in this exponential, and now we know how these modes would propagate. So that's what comes out of calling Eig. So visually, I mentioned that these columns are our modes. So we can envision our eigenvector matrix looking something like this, where we have our first order mode and second order mode, third order mode, and if we overlaid this on top of whatever waveguide we were analyzing, we could see our modes superimposed. And here's the x direction. So as we see in our coordinates, x direction, and y is the direction that we're propagating. Now, if we have, let's say, 200 points in the cross section, we will have 200 different modes. Not all of them correspond to guided modes. Other ones correspond to waves that are leaking out of the guide or just passing through it or doing something else. Only a few of those are actually guided modes. So here's the MATLAB code. And we build a function called EZ-mode, which calculates modes in a slab waveguide for the EZ mode. We have three inputs. We give it the permeability XX, permeability YY, and the permittivity ZZ. We also give it the normalized grid resolution. This is the K0 times dx. And that's all this needs to calculate all the modes. So what comes out is it'll automatically select the fundamental mode and come out as EZ source. It'll also tell us the magnetic field component of the source. It tells us that effective refractive index. But what also comes out is all of the modes and which one of those is the fundamental mode. So it has automatically pulled off the source terms and calculated its effective index, but it also gives you all of the modes and the index of which one's the fundamental mode. So the first thing we do is we look at how big our grid is in the x direction. So we just look at the length of one of those. We could have used any three, URXX, URYY, ERZZ. I was in the mood to choose ERZZ here. Then these come in as one-dimensional arrays because we extract them from our 2D grid on finite difference time domain. Remember, we need to diagonalize these. So we stick them into a diagonal matrix, and we also make that matrix sparse. And what that does is it doesn't really store anything that's zeros. It just stores the non-zero elements. So this matrix takes up a whole lot less memory storing it as sparse. Then we go ahead and we build these derivative operators. Notice they really just have two dominant diagonals. So that's what's happening. I'm using SP-diags to insert those dominant diagonals. And I create a DHX and DEX. It turns out those derivatives look a little bit different for E and H's because we're using a Yee grid. They're staggered. So how we do finite differences to approximate the derivatives looks a little bit different just due to the Yee grid. Well, once we have the derivatives and our materials matrices, now we can build the eigenvalue problem. So we calculate our A and B of the generalized eigenvalue problem. We solve it, and out comes all of our eigenvectors and all of the effective refractive indices. However, at first they're squared, and it's also a big square matrix. So diag extracts the diagonal, so we just have a 1D array of all our effective refractive indices, but it's still effective refractive indices squared. So we take the square root, and we convert this to just a linear array, a one-dimensional array of all our effective refractive indices. Now we need to find the fundamental mode. And so what we do is we look for the largest effective refractive index, the largest real component. The one that has that is our mode, is our fundamental mode. So we pull that one out in terms of EZ source. And then we go back and we look at the finite difference equations, and we had solved for the HX component. And we can reuse that equation to calculate HX source. So now we have the E and the H components of the source. And that's it. This little function's over. So it's pretty compact, it's pretty simple, and I did touch on the theory of what's behind here, but really we'll cover this in much more detail in the following class, Computational Electromagnetics. So if you wanted to write your own, you can try. Here's something to benchmark off of. We have a core that's 3 wavelengths wide and has a refractive index of 2 embedded in air. So the surrounding refractive indices are 1.0. And we're calculating the fundamental mode, and we see that it has an effective refractive index of 1.99. Remember, the way we're identifying this is looking for the largest real value. So that's clearly the largest. And so then we have our second order mode, third order, fourth order, fifth order. And if for some reason we made this core skinnier and skinnier, at some point these higher order modes would drop off. And there'd be at some point where the mode would be skinny enough that only this fundamental mode exists. And that's called a single mode waveguide. That's usually what we're interested in. Although some folks are getting interested in slightly multi-moded waveguide because they'll put different information on the different modes. And then if we made the core even smaller, at some point even the fundamental mode gets cut off and nothing interesting happens in a waveguide like that. Okay, so we discussed some quick theory with slab waveguides. I stepped you through quickly how to analyze a slab waveguide to calculate the modes and gave you all the MATLAB code to do that, and hopefully just enough understanding to sort of believe what's happening in that method. And you can use that code to calculate sources, or calculate the modes. So given those modes, now we need to figure out how to include that in finite difference time domain as a source. So we're going to inject these sources the exact same way with a rather minimal modification to our total field scattered field framework. But let's remember what this means. We have a region called the total field that contains the source and anything that gets scattered reflected from the object. So the total field is what is in our lab. That's physically real. If we numerically remove the source up here, all we see is what gets scattered from the device. In a sense, think of this as launching a one-way source at the object, and then it scatters and can pass transparently through that interface. So we just declare this is so, we write our finite difference equations consistent with that, and everything should work. And we know by now that the two problem areas are at the 2 layers of cells on either side of the total field scatter field interface. On the scattered field side, our finite difference equations contain a term from the total field side, and we have to subtract the source from that to make it look like scattered fields. And on this side, on the total field side, our finite difference equations reach over to the scattered field side, and we have to add the source to it to make it look like a total field quantity. And once we incorporate those corrections, we suddenly get a one-way source. So how do we do this? Remember, first we just calculated a Gaussian as a function of time, and we called that our electric field source. And then we calculated what the magnetic field component of that should be. However, it's a half cell away and a half time step away, so there's a time step. Also, we're injecting this potentially inside some material that has an impedance, so the amplitude of that H field is different than up here. We just gave it unity amplitude. So we give it this so that it satisfies Maxwell's equations, and we give it this time delay to compensate for what's going on the Yee grid and our time finite differences. So let's look at this a slightly different way. We have the electric field, which is our Gaussian source, the magnetic field, which has a different amplitude, and our Gaussian source, and we lumped everything into this time delay delta t. So calculated on the previous slide. Now for our waveguide source, here's what's going to happen. We have a ramp function that we'll talk about in a bit, but just pretend this isn't here right now. We just analyzed the slab waveguide through the cross-section FDTD grid, and we came out with our Eigen-Vectors. So we look at the electric field component of the Eigen-Vectors. So for the Gaussian source, for the fundamental source, this looks almost Gaussian, but we could have a second or third order. That's this amplitude function. That's what it looks like in the cross-section. We've also calculated its effective refractive index, so we know how it propagates. We also know that it oscillates in time. So the magnetic field source, we'll give it the same ramp function that we'll talk about, but it has its own amplitude cross-section, and we calculated this from our EZ mode function that we wrote. So both of these come out. We don't have to worry about scaling it according to the impedance. That comes out of the finite difference analysis of the waveguides. Remember, EZ source and HX source came out of that function. So we have those, nothing to worry about. It also oscillates as a function of time, but remember this delta t that we calculate, we have to put this in because this is a half cell apart and a half time step apart. So this starts to look like our pure frequency source. And remember what we had to do with our pure frequency source. We didn't want to just turn it on and slam into it. That's a huge discontinuity in time. We sort of eased into it. So that's the purpose of this ramp function. We want to ease into that source. And you'll see that in some movies following. So at first, we won't know anything about our waveguide finite difference analysis. We think we're doing a two-dimensional finite difference time domain simulation, and we will. So we build our grid, we build our PML, we build the waveguide on it, and here maybe we're studying a waveguide bend. We want to launch energy into our waveguide, we want to see it go around the bend and exit. And maybe we're studying how much of that is leaking out so we can figure out how tightly we could bend our waveguide without losing the energy. So what we'll do is we'll look at this little window in the cross-section of our grid. And this is what we'll analyze in our finite difference method. We'll look at that cross-section and calculate all of the modes that exist. And we'll use that to source the waveguide. We'll do another thing. We will also analyze the cross-section on the exit side. We have to do another analysis because whatever comes through here probably won't look like our pure fundamental mode anymore. And what we want to do is use the modes we calculate here to sort of weigh our simulated field against the modes to figure out how much power is in each of the mode. And then the waves would hit the PML and get absorbed. So a real simple example of how we could model a waveguide circuit. So here's an animation of what this would look like. So we see the green profile source up top, and notice that that source did not immediately turn on. It sort of eased into the source. We could see it kind of going around the edge, but a lot of it is leaking out. And of course, whatever leaks out hits the PMLs and gets absorbed, so it doesn't reflect back in. And then that blue line on the right is just tracking in real time the fields leaving on the right-hand side. Now, what we would probably want to do is be Fourier transforming that blue line to get the steady state field, and then that's what we'll compare against our finite difference analysis to figure out how much energy is in each of the modes. Let's play this again, and let's look at how the source turns on. It sort of eases on. We don't just click it on and it's on full blast. We ease into it. So that's very important. So one thing we can conclude from this about looking at it is this is not a very good waveguide bend. We're losing a lot, clearly. Now, maybe there's some strange reason we would want that, but probably not. So this is a bad design. Good simulation, bad design. Okay, onward. Our next topic now, we have an idea of how to calculate the modes. We have an idea of how to modify our total field scatter field framework to inject the modes. Now we need to figure out what's coming out. So given this crazy field at the output, which no longer looks like our pure single guided mode because it's leaking out, how do we figure out how much of the guided mode is in that? I hinted to it a couple slides ago. We saw sort of a real-time update of the field exiting the face, and I said we Fourier transform that to calculate the steady state field. In this case, we are illuminating our waveguide with a pure frequency. And if you've run any simulations now with these Fourier transforms happening, you can appreciate that that actually does slow things down a bit. Now, for a pure frequency, we can do a trick here that prevents us from having to perform these Fourier transforms during the whole simulation. We can turn on the simulation and we can let it run. And we let it run until everything reaches a steady state. That previous movie you saw, that reached a steady state probably somewhere around halfway through the simulation. We see that initial pulse come in, kind of come around the bend, but at some point it's really looking the same and it just repeats every wave cycle and looks the same. So what we can do is wait until we reach a steady state and just do our Fourier transform over one cycle of the wave. And so we can get simulations done a bit faster that way. It's a little bit faster for calculating steady state fields. Or you can do it just like we've always been doing it. That's not a problem. But if we want to do that, we just modify our Fourier transforms. So we're just integrating over one period of the wave. And so it looks kind of similar, but we only have to do this over one period of the wave, which is kind of neat. So here's the MATLAB code for doing this sort of revised Fourier transform. Before the simulation even begins, we'll calculate the period of the wave. Then we'll calculate how many time steps are in one period. And what we want to do for best accuracy then is actually change the time step, make it a little bit smaller, so that won't hurt our accuracy. If anything, it's improving it because we're making it smaller. But we make one period exactly an integer number of time steps. So that helps the accuracy in our integration. Then while the FDTD code is running, we'll add code something like this. So if t is the thing that goes 1, 2, 3, 4, 5 for the time steps, nt is the number of time steps for one cycle, what we'll do is in the last nt steps is then start calculating our Fourier transforms. And there's some terms missing here. So after the FDTD loop is done, we finish off our Fourier transforms. Very similar to what we did before, just slightly different expressions because we've modified our Fourier transforms to just integrate over one period. Okay, so we run our simulation and we calculate the steady state fields at the input slice. So in other words, what's getting reflected, and the output slice. So in other words, what's getting transmitted. And we get this actually came out of the simulation. Notice these numbers are 10 to the minus 16. So this is really just noise. So we don't really see any reflections coming back from this circuit. If it were a tighter waveguide bend, we might see some reflections. But we do see a good amount of transmission through this. Not pure transmission. There's certainly some waves being leaked out, and we see that in terms of oscillations outside of the guide. And we excited it with a unit amplitude source, and we're getting out an amplitude now of about 0.34. So it's lower because power has leaked out. There's just less left in the waveguide. So the question is now, what's going on here? What is the amplitude of the fundamental mode, and how do we separate that from everything else going on here? Or did we excite the second order mode? How do we figure out the amplitude of what's now in the second order mode? Even if we didn't initially excite it, any kind of discontinuity in our waveguide could transfer power from the fundamental mode out to those higher order modes somehow. How do we distinguish that? And that's what we'll talk about next. So, we can calculate all of the modes in our guide using that Eigen-Value problem. We can run our finite difference time domain simulation and calculate the field in the cross section, which could look crazy. Well, no matter what this looks like, it has to be some linear combination of these eigenmodes. So if we multiplied our fundamental mode by some complex amplitude term A1, we multiplied our second order mode by some complex amplitude A2, and so on, we added all of these up, there has to be some set of weights that gives us this field. So the trick is, given this field that we simulated in finite difference time domain, how do we calculate the amplitudes, the complex amplitudes of all of those modes? Well, let's look at the numerics. So this overall field, this is a cross-section of our grid, so it's a whole bunch of numbers stored in a column vector. What does that equal? It's a linear sum of our Eigen-Modes. So this is the Eigen-Vector matrix that we would calculate from that Eigen-Value problem. And we know that the columns are the modes in the waveguides. Now, while I'm showing it as mode 1, mode 2, mode 3, that's not necessarily the case. They could be in a scrambled order. That's not so important right now. But for simplicity here, let's just pretend they are in order, mode 1, 2, 3, 4, 5. Then they have their amplitude terms in a column vector. So if we multiply this big Eigen-Vector matrix by this, here's what we get. We get that amplitude term times the first column in the Eigen-Vector matrix, the second amplitude term times the second column, and so on. And in fact, we'll probably have hundreds of modes here, and so this is a very, very large expansion. What we want to get is the A1, A2, A3. We'll know the modes from our finite difference analysis, that EZ mode function we write, but how do we know the amplitudes given the field that we calculated at the output from our finite difference time domain? And that's what we'll do on our next slide. So, we have our Eigen-Vector matrix that came from our Eigen-Value problem. We have this column vector of unknown coefficients. And here's what our finite difference time domain told us the fields look like on the reflected side. Similarly, on the transmitted side, we have our eigenvectors. We have these unknown coefficients, which are the amplitudes of all these different modes. And here's the field on the transmitted side. We know what it looks like after our finite difference time domain simulation. These are the steady state fields that we Fourier transform to get. So on the reflected side, this EREF term looks like this. And on the transmitted side, our ETRN term looks like this. Well, we simply take these equations and solve them using linear algebra for AREF and ATRN. So we'll know these two terms from our finite difference time domain simulation. We know these two terms from our finite difference analysis of the Slab waveguide. And we can do this simple little trick to calculate these amplitude terms. Once we have that, we can calculate how much power is in each of those modes. We simply take this column vector of amplitudes and divide by the amplitude of our applied wave, which is probably just 1. So really, Pref is just Aref absolute value squared. And we can do the same thing on the transmitted side, and we will have all of the powers that end up in each of the different modes on the transmitted side. If we're interested in only one mode, the fundamental mode, for example, we can just use these simple equations. We'll just pull off the amplitude coefficient corresponding to the fundamental mode and divide it by the amplitude of our applied mode, which is probably just 1. And then the same thing on the transmitted side. The amplitude of the fundamental mode on the transmitted side divided by the amplitude of the applied one. And so now we can calculate the power coming out in the fundamental mode. So that's how it's done. It's actually pretty easy. There's some work done in that finite difference analysis, but once we have all of those modes, we can weigh it against the fields that we simulate in the cross-section and figure out the weights on each of those modes. So here's the MATLAB code from what we talked about on the previous slide that implements what we talked about on the previous slide. And we're trying to calculate these amplitude terms. So we grab that Eigen-Vector matrix. This is a big square matrix containing all of the modes in the cross-section. And we divide it by the simulated field in the reflected cross-section. So EREF is the reflected fields in that cross-section at the input side of the guide. ETRN is the field at the output of the waveguide. So these are the Fourier transformed EREF and ETRN. And EZT are the modes on the transmitted side, the big Eigen-Vector matrix there. So we do our backward divide and we get these amplitude terms. And also from that function EZ mode came an output argument, something like ind, that told us the index of the fundamental mode. So if we have that, we can go inside AREF, for example, to that ind and pull off the amplitude then of the fundamental mode. We take the absolute value and square it, and we have the reflectance of the fundamental mode. And we do the same thing for the transmitted side and have the transmittance. Now we should be dividing by the amplitude of our source mode, but usually we make that 1, and so then it doesn't need to appear in these equations. So at this point, ref and TRN shows us the fraction of power reflected into the reflected fundamental mode and transmitted into the transmitted fundamental mode. So here's an example calculation where we run a simulation. It does its finite difference time domain stuff. Here's the field on the input side. Here's the field on the output side. Once we weigh this against, let's on the transmit side. Once we weigh this against our Eigen-Modes, here's the amplitude coefficients that we calculate. Clearly, we see we have a lot of energy in one of the modes. That's probably the fundamental mode. But there's also power in other modes. So this number is 10 to the minus 16, so reflectance is essentially 0 here. But what's the transmittance of the fundamental mode? We sourced it with an amplitude 1 in the fundamental mode. So we have a 1 in the denominator. We have the 0.87 in the numerator. So in this particular waveguide circuit, we actually got 76% of the power coming out still in the fundamental mode. Kind of amazing looking at what's down here. So this is 24% of the power that's being leaked out. So if we do this type of analysis, here is some numbers that we can do a benchmark simulation. We're doing this for a wavelength of 1.55 microns. The width of the core is A, which we've set to 0.5 microns. The cladding material has a refractive index of 1.5 and the core has a refractive index of 2. So that's everything we need to know to set up the model. And then we have 3 simulations running left to right. And we have a tight bend, a less tight bend, and even a lesser tight bend. And we look at transmission. So when the bend is 20 microns, we see that the transmission is about 90%. So 20 microns, that's huge. And this is a big problem in integrated optics, is that these waveguide bends need to be huge so that we don't lose light. And there's actually been a lot of research looking at photonic crystal waveguides that can do very tight bends without losing power. So anyway, use these if you build this type of code to benchmark yourself and see if you get these same types of numbers.